So, what actually happens when we recycle concrete again and again? It's one of those questions that kind of forces us to completely rethink how we look at building materials. I mean, we already know how to recycle concrete once, right? But what if we want to create a truly closed-loop sustainability system? A system where the end of a building's life is literally just the beginning of another, over and over again.
Welcome to this explainer. Today, we're going to take a calm, deliberate journey into the deep material science of concrete waste. We're exploring the fascinating and, honestly, sometimes pretty challenging reality of multiple-time recycling. We really want to understand what's happening at the microscopic level when we ask our building materials to serve generation after generation.
Here is our roadmap for today. 1. The zero-waste concrete loop. 2. The attached mortar problem. 3. Physical property degradation. 4. The impact on fresh concrete. 5. Long-term durability shifts. And 6. Making multi-recycling work.
All right, Section 1, the zero-waste concrete loop. We are essentially redefining recycling for the future here.
Let's just trace the typical lifespan of concrete waste. When we crush it that very first time, we get what's called first-generation recycled coarse aggregate, or RCA1. But if we stop there, it just becomes waste for the next generation. True sustainability means we have to take that RCA1 concrete, crush it again to make RCA2, and then RCA3, and so on. This is the multi-recycling paradigm. It's a zero-waste cycle, where identical products are reproduced in a continuous, never-ending loop.
Moving on to Section 2, the attached mortar problem, because, well, the reality of the recycling process is a bit more complicated. An infinite loop sounds absolutely perfect in theory, doesn't it? But the physical reality of crushing rock introduces a primary culprit that fundamentally alters our recycled concrete. We call it attached mortar. This is the residual hardened cement paste that stays completely glued to the original aggregate even after the concrete is crushed. To really picture this, imagine that attached mortar as a highly porous sponge. It tightly grips the solid stone inside, and it absolutely refuses to let go, no matter how many times you run it through a crusher. And here is where it gets really interesting, because this sponge actually grows over time. By the time we reach the third generation of recycling, this attached mortar can make up over 60% of the aggregate. Just think about that for a second. Natural aggregate has exactly 0% attached mortar, but your multi-recycled aggregate, it's predominantly made of this old, hardened, porous paste. That brings us to Section 3, physical property degradation. Let's look at how the aggregate actually changes. We have to understand how this ever-growing sponge fundamentally alters the physical properties of the aggregate across all these generations. So let's contrast the materials. Natural coarse aggregate is incredibly dense and hard, with super low water absorption, usually just around 0.32 to 1.8%. But because of that 60% mortar buildup acting like a giant sponge, our third-generation recycled aggregate sees its density reduced by up to 24%. And the water absorption, it spikes massively, reaching up to 11.2%. The material has quite literally become lighter and a whole lot thirstier. And it's not just about the weight in the water. Repeated crushing across multiple generations takes a heavy physical toll. The sheer force of the process creates these tiny microcracks deep within the aggregate. Because of that, the abrasion resistance and the crushing index consistently weaken over multiple cycles. In short, the multi-recycled aggregate just becomes increasingly susceptible to physical wear and tear.
Section 4, impact on fresh concrete. The ripple effect on new mixes.
So, what happens when we actually take these spongy, degraded aggregates and try to mix them into a brand new batch of fresh concrete? Well, there's a profound ripple effect. Let's walk through the chronological degradation here. In cycle 1, because the aggregate acts like a sponge, it immediately drinks up your mixing water. This causes the concrete slump, which is basically its flow and workability, to drop significantly. You literally have to add more water just to mix it. By cycle 2, the porosity is so high the trapped air content begins to rise. And by cycle 3, the air content can reach up to 4.4%, compared to roughly 3.4% in natural concrete. It becomes this thicker, much more difficult mix to work with, absolutely filled with microscopic air voids.
Section 5, long-term durability shifts, strength and shrinkage over time.
Once this fresh, highly absorbent, multi-recycled concrete finally hardens, we have to look at the long-term consequences for its strength and stability. Compressive strength is the fundamental property of hardened concrete, right? And there is a clear degradation here. In cycle 1, it retains about 82 to 96% of natural concrete strength. Cycle 2 sits between 83 and 93%. By cycle 3, it can drop to anywhere between 57 and 90%. But notice something important. While the degradation is undeniable, the drop gradually stabilizes between the second and third cycles. The material finds a new, albeit lower, baseline.
Now let's see how this builds into other long-term issues. Because of the higher porosity and those weak transition zones between the old mortar and the new mortar, the concrete tends to shrink more as it dries. This increased drying shrinkage, along with all those extra air voids we talked about, means it's much more vulnerable to water and chloride penetration over the years. The structural integrity is essentially tested far more severely by the elements.
Finally, Section 6, making multi-recycling work, finding the equilibrium.
Please don't be discouraged by all this. We can absolutely engineer our way through these physical limitations and find a working equilibrium. Here are the proven mitigation strategies we have. First, we carefully adjust the extra mixing water to compensate for that thirsty aggregate. Interestingly, this can actually provide beneficial internal curing later on as the water is slowly released from inside the sponge. Second, we use an equivalent mortar volume, or EMV, mix design. This is a really smart technique where we deduct the amount of new mortar by exactly the amount of old mortar attached to the aggregate, which drastically reduces shrinkage. And third, we can simply reduce the recycled replacement rates, blending natural aggregate back into the mix to restore overall strength.
And this leads us to a highly reassuring takeaway. Research confirms that, quote, even when no strengthening methods are applied, multi-recycled concrete can be used as normal strength, like 20 megapascals, as well as high-strength concrete, like 50 megapascals. So, despite the physical degradation of the aggregate, multi-recycled concrete easily meets the 50 to 100-year design life requirements for standard everyday construction. We've seen the science. We understand the physical changes, the whole sponge effect of the attached mortar, and exactly how we can engineer around those limitations. Which leaves us with one final, pretty profound thought. As our buildings age, will our cities become the self-sustaining quarries of the future? Thank you for joining me for this explainer. Until next time, keep pondering the true shape of a sustainable world.